Hello, this is Siri, and today I would like to present the efficient sentiment analysis using encoder-only transformer model. And we are a team of three, and this is Siri Yelu, and my other teammates are Rohan Jonalagada, Srinidhi Kandimala, and our advisors are Professor Shenzhao. And yeah, on proceeding with today's presentation. So today's agenda is to present the introduction, dataset, encoder model, hyperparameters used in the project, results, and conclusion for this PowerPoint presentation. And for the first slide, if we look at the introduction for the project, so to begin with the sentiment analysis. So sentiment analysis is basically an essential application in the natural language processing, which identifies and categorizes opinions in text as positive, negative, and neutral. In today's digital landscape, sentiment analysis is a vital tool for organizations striving to understand the public opinion, especially on social media platforms, leveraging the natural language processing, where sentiment analysis helps the companies to interpret user sentiments into the positive, negative, and neutral categories so that they can do the evaluation based on that, which is expressed in vast amount of text data. This project mainly centers on sentiment analysis in the context of corporate layoffs, which is a sensitive subject that spark as a substantial discussion across the platforms like Twitter and LinkedIn. And in social media, sentiment analysis, however, poses a unique challenges due to informal language, abbreviations, and sarcasm, which leads to complicating the interpretation of traditional models. And to overcome these obstacles, this project uses encoder-only transformer model, which is an advanced NLP architecture capable of capturing nuanced data, which is a context-rich representations in text. The model is trained on Twitter dataset and tested on LinkedIn dataset, assessing the cross-platform robustness. Additionally, word-to-vec embeddings are used to convert text into numerical vectors, which enhances the model's ability to interpret sentiment accurately. Extensive data cleaning and preprocessing ensures high-quality inputs, enabling the model to provide accurate and adaptable sentiment classifications and offer valuable insights to public perceptions of corporate layoffs across social media. And coming to the data set used in this project, is we have used two data sets, that is the Twitter data set and the LinkedIn data set. And as we see this, the project leverages two data sets for sentiment analysis, one from the Twitter and another is from the LinkedIn. These data sets are stored as processed twitter.csv and the processed linkedin.csv in the project, which is the code we have attached in the submission, and are loaded into the pandas data frames for the further processing. This cross-platform approach ensures that the model can generalize across different types of social media content, with Twitter data serving as a training set and the LinkedIn data reserved for the testing. And we have performed the dataset cleaning in the project. To ensure high quality data, each dataset has undergone through the following cleaning steps. And the first step is tokenization. In this step, we have clean text column, which basically contains the pre-processed text data, and it is tokenized by splitting each entry into individual words. This tokenization process is applied separately to each dataset, that is the Twitter and the LinkedIn. And the second step performed in the dataset cleaning is stop word removal and lowercasing. While not explicitly shown in the segment of code, it is common in such preprocessing to lowercase the text and remove the stop words before tokenization. If this has been done prior to tokenization, it ensures uniformity in the vocabulary and reduces the noise from common but uninformative words. We have also done the word vectorization. This is used to convert the text into numerical form, which is used to create a dense vector representation for each word, where two word-to-vec models are trained independently on Twitter and LinkedIn tokenized text to capture the unique linguistic characteristics of each platform. And the model creation is like trained on the tokenized Twitter dataset and trained on the tokenized LinkedIn dataset as shown. And the word-to-vec parameters used here are vector size equals to 100, which probably generates the 100-dimensional vectors for each words, balancing the semantic richness with the model complexity. Where we have set the window to 5, which considered a context window of 5 words around each target word, allowing the model to capture context effectively. And the minimum count has been set to 2, in which the words appearing fewer than twice are excluded to focus on frequently occurring words and reduce noise. And the workers have been set to 4, which enables multi-threading with 4 threads, which speeds up the training. and the sentence vectorization has been done in the process. While not fully implemented, there is an indication of getC function that likely aims to create the sentence vectors by averaging the word vectors of each tokenized sentence. Find this step is common in LLP to represent the entire sentences or the document in a way that preserves the overall semantic content. From the next slide, my friend Rohan will continue. Thank you.
Thank you so much, Siri. Good afternoon. My name is Rohan, and I will start my presentation from the most important part of our study, which is an encoder model. And I will be talking about what is an encoder model and what makes it different than rest of the machine learning models. And also, following up, I will be talking about a little about the model architecture, the the one we have used in our project, and also a little about the hyperparameters that we have used, and also the hyperparameter tuning that we have done using the Optuna. And at the end, we are going to talk about the results that we have gotten, and we are going to compare in the we are going to compare the encoder model with the rest of the other machine learning models. Um, so going on, so answering the question, what is encoder? Encoder is an component. It's in a transformer-based neural network that process input sequence and transform them into a meaningful representation. So what encoder does is it captures the dependencies between the input sequence, and uh, for our study we have used an encoder model such that we have used it for classification. uh, we are in the encoder model, we are trying to capture all the dependencies from the input sequences and try to use that information to predict what the sentiment at the end. So here the usually the encoder's role is to analyze and understand the input data and capture the interdependencies in important information like relationships and also the pattern among the sequence words. So what makes it different is the encoder model adapts a self-attention mechanism, which I will be talking further in this presentation. So, and the other part is it also allows the parallel processing. So, instead of going one word at a time, it takes the input as all at once and try to capture the dependencies between them and try to make a relation map between the inputs all at a time. So that saves a lot of time, and it has a and and going to further. So let's talk about the architecture. The model that we have used contains these seven parts. So at the beginning there are word-to-vec vectors, which is came from our dataset. So after getting the vectors, these vectors are passed into an embedding layer, which in fact try to convert them according to the model. So which is after going through the embedding layers, the positional encoding has been applied to all the vectors. So the position encoding adds up the position which the model can know the position of the sentence. So after going through, there will be a stack of encoder layers. Each encoder layer consists of two parts, which is attention layer and also the feed forward neural network. The output of the positional encoding will pass it directly into the attention layer, which captures the attention scores and and forward it into a feed forward neural network. The output of the feed forward neural network would be again passed into an attention layer if there are stacks of encoders. So at the end of the encoder layer, we have applied a final layer, which would be including a linear layers. So stack of linear layers. So after getting the final layer, we have used the softmax function, which computes the probability of each of the predictions. Like we have for the sentiment analysis, there are three labels which we 0, 1, 2, which represents the sentiments. So the softmax function predicts the probability of each label, and at the end of to predict the label, we have used the argmax function. So I'll be going through each part in this presentation and try to explain a little bit more. So going with the word vectors. So after data splitting for the training, testing and validation, so the future part which are going useful for the training contains the 100 columns, which are the vector representation of from the word to vec. So these are the vector representations. So additionally, there is another column which is sequence length. This determines the total number of words present in each sentence. This will be useful for the model to know how many words are here in the sentence itself. That's how that would be useful to predict the that would be useful to capture the attention. So uh, the padding token, which would be here, there are 100 vectors. This would be repeating until the sequence length, and after the sequence length, it would be 0. That's how we have used a mask and try to multiply with it such that these gonna be 0, so that it only captured the attention from the required number of words, from the words in the whole sentence. So there's one more thing that we have done is for the training part, which we have used for Twitter dataset. Hardly has words, hardly have a total number of words of 50. But for the testing part, which we have used for the LinkedIn dataset, they have the words approx 350. So that's a lot in a sentence. So what we have done for even for training itself, we are trying to use the maximum length. The maximum length is 500, and try to compute the model. So going further, after getting the after the padding, the vector is going to be in a stack and will be passed into an embedding layer. So each input sequence would be max sequence comma n, where the max sequence represent the maximum sequence, and so uh, the number of, so it will be passed into an embedding layer. In an embedding layer, there are one linear layer, which is the number of input dimensions comma d model, and also a layer normalization. So from here, n is nothing but the 100 100 vectors. So the input shape would be 500 comma 100 for the study that we have done. So these are passed parallelly into embedding layer, the linear to the linear function. So the output shape would be max sequence comma d model. So these output would be passed into the positional encoding layer. So in the positional encoding, the input would be the output of the embedding layer, which is a max sequence comma d model. This would be passed into an encoding, positional encoding, and they would be added. They have been assigned with specific positions using a sine and cosine functions, which would be having if even number of layers would be sine, and odd numbers would be cosine. So that's how the model knows the sequence of the sentence of the vectors. So after going through the positional encoding, the output would be remain the output dimension would be remain same, but the positions got added into the vectors. So this positional encoding will pass into an encoder layer. Uh, so yes, this is the code for the positional encoding. Here there are they would be assigning a position each. They would be add up to the vectors here at the end, and after that there is a dropout layer at the before passing it to the attention layer. So going further, this is an attention layer, encoder layer. So the encoder layer is a transformer model consists of two main components, which is self-attention and a feed-forward neural network. So these encoders generally are stacked one upon other to capture complex dependencies, uh, and try to represent and try to capture the more complex data from the input tokens. So these are the input tokens that's gonna pass into, these are the output of the positional encoding, and they are gonna be passed parallelly into a self-attention layer, and the output from the self-attention layer is passed into a feed-forward neural network, and the feed-forward neural network will be passed once again into a self-attention if there's a stack of encoders. So uh, going through, this is the code for the encoder layer. We have used attention layer, and after that it would be having a sublayer connection. Sublayer connection would Sublayer connection will stabilize the training and try to prevent the overfitting, which is would be helpful for the model to learn and try to deal with the outside the testing data. So it's gonna be have a normalized and regularization values. So and also it's gonna be useful if in the back propagation. So going further, the after going through the attention layers, there would be a feed-forward neural network. So that's a, so let me before going through the attention layer, let me try to go through what is attention itself. So attention is really a key role in while we are using the encoder model. So attention is the mechanism in neural networks, particularly in transformer models, that allows the model to focus and weigh importance of different parts of input sequence, while which means that it will map the closest one. Like for example, in this diagram, there are the sentence here. For here, if we take the it value, the coloring represents the strong attention. It maps the strong attention with the and the animal. Here in later in the sentence, here in the it we cannot say what it means like in a sentence, but here it maps itself. It means the animal here that before that has been in the word that has been in the sentence itself. So that how the attention works, and this would be useful for our model to capture the past dependencies and try to map it uh, along with the other in other vectors in the input sequence. So following through, so we have implemented the masked multi-headed attention. Since we are using since we are having the maximum length of input would be 500, so we are definitely using mask to prevent to use the particular number of sequence. So this here is the input. This is the output of the positional encoding, and here in the mask attention layer. So what happens is this will be divided into three matrix: query, key, and value. I will be talking a bit in further, and this query is multiplied with the weights. I have represented all the dimensions of the query key values and also their weights, which is t model, t model. They are going to be converted into a different values of query key and query key and value. So these would be breaking down into different parts, and they're going to compute itself and try to concat at the end. This is called multi-headed attention, which is to capture more dependencies, like to capture complex dependency instead of using one type of dependency. So at the end, this gonna the heads all gonna concatenate into final one and try to multiply with the weights itself, and it will produce the output, which is the same sequence, like sequence comma d model as the input, but it will have the attention scores itself in the vector here in the head attention layer. So in the masked multi-head attention, what we have done is, after computing this attention scores, it's gonna be multiplied with the mask itself. So it only takes the attention scores which are useful and try to ignore after the sequence stops, of like after the sentence stops, it's gonna remind it won't be considered the attention scores. So going further, I will try to explain what going on in the calculating the attention scores. Here are the embedding vectors. This is the output from the positional encoding. So these are converted. These are into the queries. Each vector has their own query, key and values. Each query is multiplied with the other keys to produce a value, and this would be divided by 8, which is nothing but the number of root decay, and at the end softmax would be applied to ignore to produce a normal distribution function, like between probability function between 0 and 1. After that, it would be multiplied with the values, and at the end, this is we gonna get the attention layers, attention scores. So going through, this is the code that we have done for the multi-headed attention. So I'll be quick here. It's gonna go through the attention layer. I have a attention. So uh, the first it's gonna it will convert the normal mask into the desired shape, and try to convert and try to take the values of query, key and value, and at the end it's gonna pass to the attention part, and here the mask is also gonna pass, or is also gonna pass. If it is not none, it's gonna only take the scores which are useful and ignore which are not gonna consider, uh, and the computation does occurs at the end, and that's how it returns the uh, it returns the attention values, and after the output of the attention, it's going to pass into a feed forward neural network. In the feed forward neural network, the output from the multi-head attention, which is they have the dimensions of max sequence comma d model, is gonna pass into a feed forward neural layer, which has two linear layers in the dropout in between them. So here in the linear layer, the linear dimensions is d model comma dff. So by computing max sequence comma d model, the output from first layer would be max sequence comma dff. After that, the dropout is added. Even for the dropout part, we have these are the d model and the dff and the dropout are the hyperparameters that we have used. uh, Here, the output of first linear would be the max sequence comma DFF. It will pass into a dropout curve, and there would be no change in shape. And after that, it will pass through the second linear layer, and the final shape would be max sequence comma D model, which is similar to this. And here, this will pass into an other encoder layer, the next encoder layer, which would be having the same attention and the feed forward layer. It will be passing until the number of encoders stack upon them. So this is the code for the feed forward neural network. Here you can see that the attention scores will be going into the first linear layer. ReLU function has been applied, and after that activation function. After that, the dropout layer is applied. Like after, there would be another linear layer, and this will be the output for the feed forward network. So, and the process gonna, and it will repeat until the number of encoders stacked up on oneself. So at the end, there is a final layer. The final layer consists of two linear layers. So, and a layer normalization. So the output from the encoder would be passed into a linear layer which has the D model, D model by 2. And so the output from the first linear would be max sequence, D model by 2. And it will pass into a layer normalization. So after passing through layer normalization, there would be any change in shape. But after passing through the second linear layer, it's going to have a shape of max sequence, number of classes. For here in our in sentiment analysis, there would be three labels 0, 1 and 2. So it would be 3 here. So the output total would be max sequence, number of classes would be 3. So the max sequence is here in our study we have taken 500. So 500, 3. So going further, this is the code for the final layer. Here itself, we can see that there's a linear layers and a layer normalization. At the end, it returns the softmax values, which is the probability values for the for the labels. To classify the probability values, we have used Rmax function to particular to return the maximum probability label. So it's got and the loss function that we have used for the here you see cross entropy. So going further, uh, this is the for the hyperparameter tuning. We have used optional, which is we're gonna apply we're gonna give us some particular values for the hyperparameters, and then it gonna run multiple times and try to approach the best best values with minimizing overfitting and try to produce a real evaluation, which would be better for this project while we are training on Twitter and testing on LinkedIn, which is useful to see how real world data would be working along with the model. So the machine learning models that we have tried to train are multinomial naive Bayes and SVM and random forest classification, decision tree, and also uh, the logistic regression. And we have tried to compare these results with the BERT classifier along with our model. So for the multinomial name base, so this is the optional study. So here in the study, here in the multinomial NB, the hyperparameter is alpha value. So the alpha value is chosen between a float value which is 0.1 to 1.0. It's gonna consider every single value and try, and here we are trying to maximize the accuracy and try to run it for 100 times and capturing the best hyperparameter along with the best accuracy here. So going through, this is the result from the multinomial naive Bayes. So the best parameter is alpha equal to 0.673, and the accuracy that we have got is 0.35. Along with the accuracy, we'll try to record all the precision, recall, and F1 scores. So going further, this is the SVM, and C is the hyperparameter in the SVC. So here the kernel that we have used is linear, and the probability distribution here. So is the same though, so it's going to run for 100 times and try to maximize the accuracy and try to get the best hyperparameter for the model itself. And after getting the hyperparameter, what we did was we used the test data, LinkedIn data, to test on the model. That is the one of the reason the accuracy is low for even for every model, because it captures different values here. It trains on Twitter and try to test on a LinkedIn, which are two different types of data. So here in the SVM, we got the best parameter of C as 4.32, and the overall accuracy that we have recorded is 0.37. This is the best accuracy for after running 100 trails. So here the precision, recall, and F1 score. Going further, this we have also implemented a random forest classifier. So these n estimators and a max depth are the hyperparameters that we have trained. Here the categorical means it will either choose from 100, 200, and 300, and max depth of 5, 10, 15, and we have tried different values and tried to see if there's any change in the accuracy score by using any of these hyperparameters. And unfortunately, there is no much increase in the accuracy. And the same we have done for 100 drills and try to maximize the accuracy. So at the end, the best overall accuracy we have recorded is 0.35 for the random forest classifier. And these are the precision recall and F1 scores in the classification report. So going further, this is the decision tree classifier. The same, the max depth has been used. The criterion is log loss and try to maximize the accuracy. And it has been run for 100 epochs. So the best accuracy recorded 0.36. So these are the precision recall and F1 scores. Going further, this is a logistic regression. And here the hyperparameters are C and max iter. So this is the float function. It will take a float value between 0.1 and 10. And these are the categorical, say that 200 to 400, 600. Try to see how that's working with the model. And we have used penalty as L2 and try to run it for 100 times and maximize the accuracy. And these are the values that we have got. And the best overall accuracy that we have recorded is 0.36 along with these precision recall and F1 scores. So after these machine learning models, we have tried for BERT classifier to see how the masking function and the attention layer itself working against the machine learning models. And we are quite surprised by the results that we have got here for the BERT classifier. The hyperparameters that we have used are batch size, LR, and any epoch. One thing that I have noticed is for the BERT, word2vec is not a great fit for using BERT classifier. Generally, usually what generally people do is they try to use the BERT tokenizer, which is really good by it has a vocabulary. It chooses it gives the input IDs, and we are trying, and for the sake of study we have been trying for word2vec. So we are trying to see how well the attention layer works against the machine learning models. So that's the main motive for the uh, study. So that's how we are planning to see here. So for the BERT here, these are the three hyperparameters, and it tried to maximize the validation accuracy, which is the Twitter accuracy. So it's gonna run for 10 times, and this is the fine, and it's gonna test on the LinkedIn part. So the overall accuracy is 0.436. So, but the test accuracy is 0.477, which is higher here than the overall accuracy. And we are still trying to develop more, try to analyze what's happening in the internal in the BERT classifier. And going further, this is our model, encoder model. And here, dropout, learning rate, batch size, number of heads in the attention layers, and the demodeled DFF, number of encoders, and the number of epochs. These are the all the hyperparameters that we have used. This condition is raised because the D model is supposed to divide into number of heads. So, like in the attention layer, the D model is divided into a little parts of query key and values. So it has to be divisible. So we even take the consider the values that should be divisible. So it just in case we have put a raise here. So going further, these defining the model, encoder model, and passing it to a train function. In the train function, it's gonna take feature labels and all the batch size learning rate epochs, and it's gonna run the model and try to and try to compute the loss with the cross entropy loss, and try to optimize using the Adam optimizer, and the predict the sentiment. So this has been run for 30 times and try to maximize the best accuracy. The best accuracy is nothing but the validation accuracy here itself. So At the end, these are the scores that we have got. The best accuracy, the test accuracy that we have got, highest recording is 0.57. Uh, After here, instead of 30, we have tried for running for 50. So I think this is a result for that. So these are the rest of the accuracies, and the parameter, to the best parameters are dropout of 0.10 and the learning rate of 0.002, and batch size and number of heads, D model, DFF, and these are the values. And here itself also the validation accuracy is lower than the test accuracy. So there might be something, but we have to see further how such. So here is the results column. This has all the accuracy, precision, recall, and F score noted down here. So this is the graph that we have used: accuracy, precision, recall, and F score. So at the conclusion that even this is in the starting stage of research, and we are trying to make use of encoder attention. So we have to develop more. We are looking to develop more masked attentions, like how deeply can a attention layer capture from a sequence and can predict the output itself. So the relevant data, we are trying to gain as much as information to to predict the exact sentiment, and we'll be in the future we'll be using a different methods and try to come up with a optimized approach. So thank you so much. Thank you so much for the guidance, and the professor Shen Zhao really helped us going through all the difficulties in the project and the study itself. And also thank you for all the co-authors, Siri and also Srinidhi, for helping out with this study.